All right, so I was actually asked in lab today to go over some of the spectroscopy examples in the textbook and in the one I handed out in class in terms of benzene. So let me start by going over the example that I handed out in class. So we have a compound there whose chemical formula is C11H16. So as we talked about, the first thing you want to do is you want to calculate the degrees of unsaturation. So we're going to take 2 times the number of carbons that are present, which is 11, and we'll add to that 2. And then we'll subtract from there 16, and then we'll take that whole thing and divide it by 2. So 22 plus 2 gives us 24. 24 minus 16 over 2 is 8 over 2, and that gives us 4. And that makes a lot of sense here, because obviously we've been talking about benzene, and when you think about a benzene ring has 4 degrees of unsaturation. So we also know that what's going to be attached to the benzene ring cannot be another ring or anything that has a double or triple bond. So that's what that also tells us. But the fact that we have 4 degrees of unsaturation here is not that surprising. Now, for the infrared spectrum, really you don't get a lot of information. If you look to the left of 3000 in the infrared spectrum of this compound, you see sharp peak that reaches its minima to the left of 3000, and that would be because you have hydrogens on the benzene ring. But in terms of what else is attached to the benzene ring, really not that much information about that. So really for the IR, there's not a lot of information that we're going to get. So now we go to the carbon-13 NMR. The first thing that I notice is that there are 7 peaks that are total. And since there are 7 peaks total, but there are 11 carbons in the chemical formula, when I draw my answer, there has to be some equivalent carbons. Now, the other thing I want to notice is that there are 4 peaks in the range, I think, if I remember right, of about 120 to about 140 parts per million. Might even be, I know it's probably even smaller than that, but the fact that there are 4 peaks in this range, what do those peaks speak to? Well, essentially, they sort of talk about the carbons of the benzene ring. And one of the things that we'll sort of look at with this is a little bit about the substitution on the benzene ring. Are we talking about a monosubstituted benzene, or are we talking about one of the disubstituted benzenes, like ortho-disubstituted, or meta-disubstituted, or para-disubstituted? Those 4 peaks talk about the carbons of the benzene ring. And then the 3 peaks outside of there, they really speak to your sp3 hybridized carbons. All right. So most of the information that we get in these examples is going to come from the proton NMR. So the first thing we come across is a 5 hydrogen singlet, somewhere around, I believe it was about 7.2 parts per million. Again, if I'm a little off, I just don't have the example in front of me. I apologize, but it's in the 7s. Now, of course, this speaks to the hydrogens of the benzene ring. And one of the things that we talked about specifically with monosubstituted benzenes is that sometimes the peaks are so close to each other that the machinery doesn't necessarily know what to do and winds up essentially reading all 5 of those hydrogens as equivalent, even though technically in a monosubstituted benzene, they're not. Now, sometimes you will see the doublet and 2 triplets that you would expect for a monosubstituted benzene, but sometimes you'll see a broad 5 hydrogen singlet. Sometimes broad, sometimes not so broad, but sometimes they do come out to be a little bit broad. But anyway, the fact that we have a 5 hydrogen singlet here means essentially there are 5 hydrogens on the benzene ring. And therefore, that speaks to a benzene ring that is mono-substituted. Okay. And that makes a little bit of sense because if we go back to the carbon NMR for a second, and we talk about the number of peaks in that range of 120 to 140, where we have 4, if you have a mono-substituted benzene, and I have the branch on the upper right ring carbon, the upper right ring carbon would give rise to my first peak. The top and the bottom right ring carbons are equivalent, so that would give rise to my second peak. The upper left and the bottom ring carbons are equivalent, so that would give rise to my third peak. And the bottom left carbon would give rise to my fourth peak. So that fits that part as well, all right? So we're really looking at a mono-substituted benzene here. Now, what do we got left? We have a 9-hydrogen singlet, I think somewhere at about 1.2 parts per million. And then we have a 2-hydrogen singlet, I believe somewhere at around 2.4 parts per million. Again, if my numbers are off, I just don't have the exact spectrum in front of me at the moment. But really not so much about location, it's about what these peaks, the number of hydrogens in the integration. Now, if we start with the 9-hydrogen singlet, there's only really one thing it could be, and that would be 3 equivalent CH3s. You know, in theory, it could be 9 equivalent CHs, but that's not what you're going to have here. You're going to have 3 equivalent CH3s. So 6 carbons have been accounted for. This would account to 3 carbons, that gives us 9. That tells us that there are 2 carbons that are left. And that brings us to the 2-hydrogen singlet. Now, in essence, there could be a couple different options. You could have both hydrogens on the same carbon, but that would also mean that your last carbon would have no hydrogens because you'd have 5, and then 9 would be 14, and then these 2 would be 16, okay? So you'd have no hydrogens on the last carbon. Or you could have 2 equivalent CHs that are attached. Now, can I really distinguish which one of these 2 I have? And the answer is yes. Outside of the 120 to 140 range, we talked about that there were 3 peaks. For the 9 hydrogens, that would give rise to the first peak. Which one of these would give you 2 additional peaks? In the carbon NMR, let me just make sure I'm clear. I'm talking about the carbon NMR here. So these 3 equivalent CH3s, and I know I said 9 H's, that's why I want to go back. For these 3 equivalent CH3s, the 3 carbons would be represented by the same peak, that's 1. So now, which one of these 2 scenarios would give us 2 additional peaks in the carbon NMR? And it wouldn't be the second scenario, because if you had 2 equivalent CHs, they would be represented by the same peak. It would have to be the first scenario of having a CH2 and then a carbon with no hydrogens attached to it. So now we really have the pieces to the puzzle. Now we have to put them together. Mono-substituted benzene that has 3 equivalent CH3s, a CH2, and a carbon with no hydrogens. Right. So I'll sketch out my benzene ring. Now, one thing's for sure, I'm not going to have a CH3 directly attached to the benzene ring because then I would be finished. One possibility would be to put the carbon with no hydrogens attached. Now that leaves us with 3 CH3s and a CH2. And the only way to fill that in to give a structure that doesn't violate the octet rule, you know, and satisfies all the bonding requirements would be as follows. Attached to the carbon that has no hydrogens, 2 of the 3 CH3s, and then the CH2 with the other CH3 attached. Is this our correct answer? And the answer is no. And the quickest way to tell is that if I said to you, are the 3 CH3s equivalent here? Right away, you should be able to tell me that the answer is no. The 3 CH3s do not have the same connectivity. These 2 do, but this one doesn't. All right, and you can tell it quick because these CH3s are attached to a C. This CH3 is attached to a CH2. So this can't be our answer. The only other possible way to fill the pieces in would be to have the CH2 directly connected to the benzene ring, and then connected to the CH2, the carbon with no hydrogens, and then the 3 CH3s connected to that carbon. All right. We established the 4 ring peaks for the ring carbons. Peak number 5 in the carbon NMR, peak number 6, peak number 7. Let's do the splittings. 2 hydrogens, okay? Pick one, here's the carbon it's attached to. There are 2 neighboring carbons. Neither one of the neighboring carbons has a hydrogen. This one doesn't have a hydrogen. This one doesn't have a hydrogen. 0 plus 1 is 1, singlet. 9 hydrogens, pick one of the 9. I'll pick one from here. Here's the carbon it's attached to. Here's the only neighboring carbon. It has no hydrogens. 0 plus 1, 1, singlet. And therefore, this structure is your answer.